please welcome Robin, the creator of BitVM, on stage. All right, well, it says I'm the moderator. I'm just here to ask stupid questions, so you don't have to feel bad about it. Yeah, Robin, stage is yours.
Thanks. Okay, I'm going to give you like a very high-level overview of BitVM, the history of BitVM, the past, the present, and the future, and a high-level intuition about the key ideas behind BitVM. In general, I can say BitVM is about allowing Vitalik to retire. We want Bitcoin to take over the entire crypto market and become the single asset that does everything that all the altcoins are doing right now. Quick introduction. I'm one of the founders of ZeroSync. ZeroSync is a Swiss nonprofit organization to apply proof systems to Bitcoin. Proof systems have been a huge topic in the altcoin world, in the Bitcoin world not so much. And they are incredible, like a very magical technology, and certainly the future of blockchain technology. And so we thought it's a big issue that Bitcoin didn't really have anyone applying them to Bitcoin. So we did that, and we started that like 4 years ago. And yeah, the rough idea is that we want to improve scalability, privacy, and usability using snarks, starks, and these awesome proof systems and other cryptographic things. We're a team of 3 people mostly, Lucas, Psycho, and me. And yeah, the first thing we worked on was a stack-based light client of Bitcoin. So essentially just a way to sync Bitcoin very quickly. And then we got more and more excited about the idea of having better BTC bridges and bridging Bitcoin to second layers, because once we can bridge Bitcoin to second layers, we solve actually all the issues. Or we can solve all the issues. We can have like an Ethereum-like sidechain of Bitcoin. We can have like a Zcash-like sidechain of Bitcoin. And once we have bridges, we can essentially import any feature that any altcoin has into Bitcoin. And privacy is also a big topic, of course. Yeah, and Bitcoin staking is also a thing, like Bitcoin-backed proof of stake using Bitcoin as an asset for consensus mechanism. That's another thing that I've been working on. Yeah, the rough history of BitVM. Back in the days, 4 years ago, all we had was multi-sig bridges. You essentially just gave your money to some multi-sig, and you were hoping that they don't run away and that they don't all die, so that the bridge stays safe and alive. However, of course, this is very unsatisfactory. It's, yeah, essentially just trust me, bro. And that's kind of like the opposite of what Bitcoin is about. If you read the white paper, I think even in the abstract it says we don't want to really have trusted third parties. So multi-sigs suck. So the obvious question was, can we do better? And obviously we have seen in the altcoin world, in particular in Ethereum, snarks are just incredibly great. Once you have a snark verifier, you can build all kinds of awesome bridges and all kinds of like nice rollups, CK rollups, and side chains and whatever you have. However, snark verifier on Bitcoin, not so easy, because Bitcoin script, the scripting language in Bitcoin is very, very basic. The most awesome thing we have is like 32-bit addition. Even multiplication is a huge issue in Bitcoin script. So the scripting language is by far too basic to just implement a snark verifier in there. And that changed in 2023 when I published the Bitcoin white paper after about a year of research or so. Yeah, together with a couple of friends, I figured out a way to do essentially, yeah, to compute anything on Bitcoin, to verify snarks, and to essentially have any computation on Bitcoin. Not directly, like you don't actually execute the computation directly on Bitcoin as on Ethereum. In Ethereum, if you do a multiplication, you actually do the multiplication in the EVM and everybody does it. In BitVM, the idea was that it's sufficient if we just do it optimistically. So somebody claims this is the result, and only if it's incorrect, then you challenge them and you try to succinctly disprove them. But if it's correct, then nobody cares. It's just, okay, yeah, was correct. So we shifted the execution off-chain completely, and with that trick, we enabled a way to do arbitrary computation on top of Bitcoin. However, it was a little bit clunky, and we advanced it, and in March 24, there was the second iteration, which came up, which solved many of the issues of the first iteration. And then in October 24, we founded the BitVM Alliance, which is like a consortium of multiple companies that are building L2s on top of Bitcoin. And together, we joined forces to implement BitVM and make it production ready. And now, since stuff's never done, we even figured out a way to do way better to do way better than BitVM 2, and now there's this idea of garbled circuits and BitVM 3, which came up around April 25, and now everybody's excited about that. BitVM overview. The high-level goal, maybe the word VM is kind of misleading because people are asking, is it similar to the EVM? It's not really. The main purpose of it is just bridges. Because once we have bridges, we can bridge Bitcoin to an EVM-like chain or an EVM-like rollup and do all the EVM-like stuff on that rollup. But we don't actually want to do that on Bitcoin. So BitVM is actually just about bridges. You could do other things, but there are many trade-offs and like stuff can be expensive and so on. So the use case has really has to justify this like heavy machinery. And the only use case that I currently know of that is really worth all that overhead is bridges. And for bridges, it works well. It's better than what we had so far. So far, we had multi-sigs that are like T of n assumptions. Here we have that 1 of n assumption, and n can be like big, like 100 people or something. And as long as one of them is honest, the bridge is live and secure. One improvement over BitVM 1 was in particular that we have permissionless challenging. Like in the first iteration on BitVM 1, challenging was permissioned. So during setup, you had to specify a particular set of challengers who could actually verify that computation. And one of the main advantages of BitVM 2 was that we got rid of that, and we made challenging permissionless. And the key idea behind BitVM 2 was that actually Bitcoin script is good enough to implement a snark verifier. I just said it's not, but actually it is, since we have these great opcodes like addition. And addition is actually fine. If you just do enough additions, you can verify a snark, actually. It's just a matter of like how much effort you want to put in. And actually, if you just implement a snark verifier in Bitcoin script, you end up with 1 gigabyte of Bitcoin script. So that's gigantic and like way larger than the block size. The block size is about 4 megabytes. So there's that huge discrepancy like between the 4 megabyte block size and like the 1 gigabyte script that we would like to execute. So what we needed was like some kind of trick to essentially shrink that script in a way, or at least to execute it in a clever way such that we don't have to execute it all at once. And that's the key idea behind BitVM 2, which is essentially that you don't have to execute that script. You just commit to like a proof and an execution trace of that script, where you say, hey, like after the first step, I was at that stage, or the memory looked like this, and then after the second step, the memory looked like that, and so on. And then you commit to like a huge trace of like 1,000 intermediate steps, and everybody can read it from the chain because you have to commit to it on the chain. And if any of these steps is incorrect, or in general, if the snark proof was incorrect, then at least one of these steps has to be incorrect. And then the challengers can just pick that one step, like where they still agree, and then the next one is incorrect. So they take these two memory snapshots essentially, and then execute only that part of the script which leads from like from state n to state n plus 1. And this way, you don't have to execute the entire computation. You just have to execute one faulty step, and this allows you to disprove the entire computation if it was incorrect. And this gives us this optimistic verification of a snark proof. Actually, it's not verification, it's falsification. Yeah, I don't verify the snark, I falsify the snark. If it's incorrect, I show you that it's incorrect. It's never actually verified. If it's correct, then nobody cares, then everything is fine. And yeah, we actually implemented that in the BitVM Alliance. And we already, like we feature froze it already a couple months ago, and the security audit started it. And yeah, it's gonna be completed soon, and then it's gonna be mainnet ready. And yeah, many of the companies in the BitVM Alliance are actually waiting for that. Yeah, this is the BitVM Alliance. It's now 9 companies. Actually, Element Labs, they moved on. We lost them. They moved on to machine learning. They are doing AI stuff now, unfortunately. They were great people. Unfortunately, not in Bitcoin anymore. Yeah, but those are the people. And yeah, let's talk about the challenges. BitVM has a lot of trade-offs. First of all, the worst case cost. We already heard that in the previous talk. The worst case cost can be quite expensive because even though we are chunking the script down to like 1,000 steps, it's still quite large. Like it's still like on the order of a megabyte or 2 megabytes or something. So essentially, you have to buy a full block or like half of a block of Bitcoin. And you always have to be able to buy that block space, even if the chain is congested and the fees are high. You still have to be able to pay for that script. Yeah, and yeah, the transaction size is up to 4 megabyte. And the very important part is that you have to, or like at least this operator has to lock up collateral, because whenever they do a peg out, they essentially make a bet. They say, hey, here's my proof, and I bet nobody can disprove me. And if you can disprove me, you can take my money to disprove me. It's very important to align the incentives that a cheating operator essentially pays for his own execution. And that's why he has to lock up a lot of collateral, because he has to pay the worst case fees for like the worst case of up to 4 megabyte transactions. And yeah, that can be, depending on how pessimistic you want to be, like 10 to 100K of collateral. Also, challenges have to get crowdfunded. They are also expensive, and like the users of the site system, they have an incentive to keep the site system secure. So if there's an operator cheating, then you essentially have to crowdfund the challenge amongst all users. It's kind of like a non-interactive process, but people have to put up that money. Also, there are these non-standard transactions. I'm not sure if you know about this idea of standardness and non-standardness. In Bitcoin, there is like a difference between transactions that are consensus valid. So a block is valid if they are included in that, if that transaction is included in that block. However, they might get rejected by the peer-to-peer network for DOS reasons. For example, if a transaction is super large, then the peer-to-peer network just rejects it. I think that the largest transaction you can broadcast is 400 kilobytes or something. And we have these 4 megabyte transactions. So to execute them, we actually have to go directly to miners and ask them to put them into a block. Another big issue is that we need a light client in that bridge. Like we have to know the state of the Bitcoin system to essentially do chain introspection to see if a particular transaction was actually in the chain included. And for that, we need to run a light client in our bridge. And to make that light client permissionless is a bit of an issue. There is like a liveness versus safety trade-off. Like we have a design that is permissionless. However, in its pure version, it's resilient only against like, I think 30% adversarial hash power. So if you have more than 30% hash power, you can break the bridge and essentially drain the entire bridge, which is of course a huge incentive misalignment. And we can strengthen it, but only at the expense of liveness trade-offs. Like essentially, we have to assume that the hash rate will never drop by a factor of 4. I think. Oh, sorry, it will never drop by a factor of 2. I think the largest factor it ever dropped was like 1.6, 1.7 or so. That was when there was the miner ban in China. And if we assume in our snark that it can never drop below a factor of 2, then our light client is resilient against, like, I think, roughly 40% hash power. But in general, you have to make these liveness versus safety trade-offs. Yeah, and another issue is, of course, that the operators, they have to front the capital. So if a user wants to peg out, let's say 10 BTC or something, then it works such that the operator pays that user. He just pays out of his own pocket 10 BTC to that user. And then he goes to the bridge and says, hey, you all saw I just paid $10 to that user, and he did a valid peg out, so now I'm going to take money out of the bridge. So the operator has to front capital, which is, of course, also an issue. It can be, like, the withdrawal period can be up to 2 weeks. Also, it's a parameter, but like 2 weeks is kind of like conservative. So you have to front that capital for up to 2 weeks. So there are a lot of challenges that we have with BitVM 2. I wish we could just fork in a snark verifier into Bitcoin and things would become much easier. However, we don't stop. We keep on innovating. Oh, sorry, one point I missed is that there is a trusted setup required. Like the bridge, initially, the setup of the bridge requires that one of n setup, or like that one of n assumption that at least one of the people who participated in the bridge setup is honest, and once one of them was honest, then the entire bridge is safe. But of course, trusted setups are not very nice. And the big solution, or the great idea for solving all these problems, or most of these problems, is garbled circuits, or quote-unquote BitVM 3. It gives like 100x improvement, even like a 10,000x improvement on the disproving. And the idea is that there is a trick. We can just use a bit more fancy cryptography to just shift the entire verification off-chain. So we never have to execute any of these expensive scripts on-chain. It's quite magical. And the idea is to use garbled circuits. Has anyone heard of garbled circuits? Raise your hand. You have heard of garbled circuits? Cool. 2, 3. I bet like in a couple of years, everybody has heard of garbled circuits. As long as the Bitcoin community keeps being a bit stupid and never updates, garbled circuits will become a huge thing, I think. Yeah, most of the transaction graph stays the same, and like most of the BitVM alliance pivoted to the garbled circuits approach now because it's so superior in so many ways. And yeah, we have already implemented in the alliance a common snark verifier, like a snark verifier circuit, essentially like out of binary gates. We compiled like a snark verifier. Big shout out to Citrea in particular, the engineers from Citrea. They spearheaded that effort. And now within the alliance, many different flavors of garbled circuits are explored. Like there is a lot of trade-offs of different garbled circuit designs, and yeah, it's a huge design space, and we are exploring it very rapidly right now. Now, I talked about garbled circuits. I tried to give you a quick overview without being too technical. The very high-level idea is that garbled circuits are like a cryptographic primitive for conditional disclosure of a secret. So I got a secret, it's secret, and on a particular condition, it is disclosed, and then everybody learns it. And the condition here is I presented an invalid snark. If I present an invalid snark, then you learn that secret. So just picture a black box, and that black box is essentially a snark verifier. And that black box is exchanged during setup. Like when we set up the bridge, like all the operators, they share such a black box with everyone. And now when the bridge operator wants to do a peg out, they have to commit to a snark on-chain and essentially claim, hey, this snark is a valid snark. And everybody can just take that snark, read it from the chain, and feed it into that black box. And then that black box spits out the secret if that snark was incorrect. If that snark was not a valid snark, then this secret is disclosed. If that snark is valid, then nothing is disclosed. So knowledge of that secret acts as a fraud proof. Does that make sense? Oh, the secret is then just used in like a hash time lock contract in the chain. Like it's just if you know that secret, then you can unlock a hash lock and slash the operator. Previously, it was that you had to execute one of these huge scripts to slash the operator. Here, You just have to know that single pre-image. And that makes it, of course, orders of magnitude cheaper. Previously, you had like 4 megabytes of script. Now you have like 20 bytes or maybe 200 bytes or something. Yeah, I already explained that. So snark verifier is roughly like, it's a verify function and it takes a proof and it outputs true or false. And if, like the black box is such that if the proof is false, then a secret is revealed. And that secret acts as the fraud proof. That is the key idea, that this conditional disclosure of a secret is enough to do optimistic computation. And it's actually a super powerful primitive. Now, future research, all of that sounds a little bit too good to be true. Of course, there are always trade-offs in life. First of all, there's the circuit complexity. I talked about like just giving you such a black box, sure. How big is that black box? Well, it's like on the order of like 300 gigabytes to like a terabyte, 5 terabyte, maybe 10 terabytes, depending on like the circuit complexity, how many gates you need, and what kind of garbled circuit scheme you're using. And of course, these circuits, they have to get communicated, so they have to be sent over the wire, and also people have to store them. So that is definitely an issue, and we are thinking about different ways to like optimize the circuit size, to optimize the communication complexity. But it even gets worse. We also have to prove the correctness of the circuit, because I give you that black box, and now you're like, yeah, sure, cool black box. How do you know that it's actually a snark verifier? How do you know that it's actually the circuit that we agreed on? Well, I have to use like some stark proof or snark proof to prove the correctness of the black box, of the garbled circuit. So that is the second complexity that we have to care about. So it's not just huge, it's also a lot of compute to prove its correctness. There are different ways to prove correctness. There's also like a so-called cut and choose method, which doesn't even need any kinds of starks, but it comes at the expense of even more communication. So there are all kinds of trade-offs that we are currently evaluating there. It's very interesting design space, very interesting research going on, and many people are very excited about it, but it's not a solved thing yet. And yeah, then we can also do all kinds of interesting bridge optimizations. In particular, we can do faster withdrawals. The current 2 weeks mostly comes from this, like, what's the longest time that it would take you to get these 4 megabyte transactions into the chain? Once we have fraud proofs that are only 200 bytes, we can, of course, reduce the challenging period a lot, and that would allow much faster withdrawals. We have designs where it's reasonable to do it within like 3 to 5 days or something. And there's also an idea or like a protocol that would allow us to get rid of the fronting of capital. It's so-called transfer of ownership protocol. It comes with some trust assumptions, but the cool thing here is that the operator doesn't have to front any capital, which of course increases the throughput a lot again. Yeah, and the other thing is permissionless challenges. As I've told you, like that light client is a bit of an issue. Ideally, we would have permissionless light clients, and then challenging would be completely permissionless. But yeah, it's an ongoing research question how resilient we can make these permissionless light clients. And of course, ideally, we would also get rid of that entire trusted setup in the beginning. And that would be possible with a relatively conservative consensus change, in particular CTV, check, template, verify. It's been discussed for 5 years, and 5 years in Bitcoin is like a very short time, but it might be ripe to finally get activated within like the next 5 years. So I'm joking. I hope it gets activated within like the next 12 months or something. But that would allow us to get rid of the trusted setup in the bridge. Yeah, that's it. I don't know if I have time for questions. I don't see the Bob people more. Yeah, there's a little bit time left for questions. So should I read them from here? Okay. What's the best way to prevent 2 operators from sending the user their BTC in the same block? Well, there is an ordering mechanism. It just essentially will never happen. So how does it work? Well, the user actually, he provides an output, like a 0 value output, And he pre-signs it such that he receives 10-bit BTC. And in Bitcoin, you can sign an input and an output, and you can sign it such that other people can add other inputs. So essentially, he's saying, I give my input away, but I want to have 10 BTC for it. And then any operator can take their 10 BTC and complete this transaction, because it's actually an incomplete transaction. The user puts in 0, but he wants 10. So somebody else has to put in 10 such that it adds up at the end. And yeah, this way only one operator can spend the user's output. And this way, this is the ordering mechanism essentially. I think I will go by the likes, right? What's the incentive for the operator to process the withdrawal in the first place? Well, he gets a fee. Yeah. So the user essentially, I just said like the user signs that transaction where he says, I put in 0-bit BTC, but I want to have 10. Actually, he will say, I will put in 0, but I want to have like 10 minus, I don't know, some fee. And then the operator can execute that, but he will get 10 BTC from the bridge, and the difference is the fee that the operator gets. And of course, yeah, just a regular fee market, I'm pretty sure you guys know how that works. Why not store data for challenges on BTC itself instead of Ethereum? I'm not sure about that. We don't do that, I think. Maybe some people do something like that. I've not heard of it. What instruction set does BitVM use? Yeah, well, it's the confusing instruction set because like the first version was actually kind of close to a virtual machine, but then we just stick with the name because everybody had it already in their minds. So right now, it's not really a VM anymore. It's just like a huge circuit for snark verification. So the instruction set is actually just Bitcoin instruction set. What's the incentive to be a challenger? Yeah, that's a good question. Well, if you're a user, you should care about the security of the system. And the more stake you have in the side system, the more you are incentivized to be a challenger. And I guess like in practice, it works out such that as long as the incentives are aligned, like as long as there are enough people who would challenge you if you would go rogue, then people won't go rogue. Like in optimism and like in other optimistic systems, we have seen that challenges pretty much never occur in reality because it's just too expensive. And you're gonna certainly lose. So there is nothing to gain from trying that. If it's one of n, can the operator ever exit? Well, that's a good point. The operator can, like, yeah. The operators themselves can be federated again. So this helps. And then you can also, like, redistribute the keys of the operators without changing the setup at all. Wouldn't it be easier to to convince core devs and the broader community to add more opcodes? Well, people have tried. Like, I am very aware that this is super crazy stuff that we are doing here. Like, this is absolute bonkers. No question about that. And the only reason we are doing it is because it's so hard to convince the broader community to add any kinds of opcode. Like, recently we just had like a policy change, which isn't even a consensus change. It's just how nodes relay transactions. And even that was like the biggest drama ever. It's Bitcoin community, like in Bitcoin, toxicity is layer 0. Everything is built on toxicity. And that's a good thing. It's also a bad thing. It's pretty draining for developers, but yeah. Maybe at some point we will just solve witness encryption or something to yeah, solve all these issues just on the crypto level. Yep. Yeah, CTV, check template verify, like that basic covenant thing, that is extremely useful for us. As I said, it allows us to get rid of the entire trusted setup. And I think it's the least controversial upgrade that is currently discussed. I mean, there are many others. One thing that would be great would be just big int arithmetic. Then we could just verify a snark essentially in Bitcoin script in like, I don't know, 10 kilobytes or something. Yeah, there are many others. Then there's opcat, concatenation of two strings. That's a huge topic, of course. It's pretty controversial because it's hard to say like what are like the second order effects of it. Oh, surprisingly, it enables everything. It's like, in particular, you can use it for covenants, but you also can use it for, it's the missing ingredient to verify Stark proofs, because Stark proofs are mostly like Merkle pathed. And if you can concatenate bytes, then you can verify Merkle paths. And once you can verify Merkle paths, you can verify Starks. Yeah. Did you try implementing a transparent Stark verifier? Well, not really. Actually, the verifier themselves, that would be much smaller. The issue is that you have to commit to the proof, and currently we are committing to the proof in so-called Lamport signatures, and Lamport signatures are huge. That's essentially the only way we have currently in Bitcoin to introduce state into a Bitcoin script. And yeah, they give you like a blow up of, I think, don't let me lie, 25 bytes per bit. And Stark proofs are already on the order of like 100 kilobytes or something, and now you blow that up by a factor of 8 times 26. That's like just extremely huge. You can do it, but it's very expensive. How do you make sure a challenger is honest? Well, the challenger cannot be dishonest. Like, you cannot do anything as a challenger that would be dishonest. Can you elaborate how the black box works? What is the circuit? The circuit is a snark circuit, a snark verifier. And the ZK proof system, yeah, well, gross 16 or something. How does the black box work? Well, read up garbled circuits. It's easy. Just ask ChatGPT about it. I think I don't have time enough to explain it. I would love to explain it, but it's a bit too complicated. But just ask ChatGPT; it will explain it. What changes will make the life of BitVM better? Well, I think the most important thing is to make BitVM obsolete. Like, BitVM is a pile of hacks piled upon hacks to just enable things that should actually be done by opcodes. But yeah, it's hard to change Bitcoin. As I said, like, arithmetic opcodes would totally change the game and would make everything obsolete that we are doing. Opcat sentiment, yeah, well, don't ask me about it. I think it's hard to activate it. Best existing alternative to BitVM, in my view. There are other flavors of BitVM, like BitVM X, and there's Bitcoin OS and stuff like that. It's very similar in spirit, but I think those are the best alternatives. And then, of course, you can have multi-sigs. Do arithmetic opcodes bring risk to the system? Well, big int arithmetic is essentially equal to concatenation. You can do mostly everything you can. It depends on like the byte size that's of the integers that you can add. But if you can add arbitrary size integers, it's essentially the same as concatenation. Still need simulated covenants in BitVM 3, yes, but less, not that many. So CTV would still be a big improvement. Thank you.